Let's take a look at doing some basic moisture calculations. The moisture content of fresh fruits and vegetables is an important consideration for anyone who is about to dry them. This tells you how much moisture is present at the start and allows you to calculate how much water you need to remove in a particular drying operation. Usually, the moisture content of materials is expressed as a percentage on a weight basis. We have already used 85% as the moisture content for mangoes. This means that 85% of the weight of a given sample of mangoes is water. Since the total sample constitutes 100%, we know that the remaining 15% of the mangoes is something else. The remaining 15% is solids. An easy way to think of the composition of fruits and vegetables is, if it isn't water, it's solids, or if it isn't solids, it's water. These solids are sugars, fiber, and other carbohydrates, as well as proteins and minor constituents. This tells us that the total weight will be equal to the weight of the water plus the weight of solids, or 100% will be the percent by weight of water plus the percent by weight of solids. So let's rewrite this and do a set of calculations. The percent water plus the percent solids on a weight basis will equal 100%. From this, we can express the percent solids as being 100% minus the percent by weight water, or the percent water will be 100% minus the percent by weight of solids that are present. These relationships will be the basis of numerous calculations for drying work. Percent water can be defined as the weight of water divided by the total weight of the sample times 100%. To find the weight of water in a sample, take the total weight of the sample and multiply it by the water content expressed as a decimal fraction. This is also called the wet basis moisture. So what is the percent water in a sample of mangoes weighing 15.00 grams if the sample contains 12.75 grams of water? Or we can reword this to say, what is the wet basis moisture content of a sample of mangoes weighing 15.00 grams if that sample contains 12.75 grams of water? This is the same problem stated in two different ways. Once again, the percent water is going to be the weight of the water divided by the total weight, which gives you a decimal fraction, and then we multiply that by 100%. The weight of the water is 12.75 grams, which we divide by 15.00 grams as the total weight of the sample, and we multiply that by 100% to get 85.0% water in this sample of mangoes. This tells us the water content as a percent by weight. In another question, we are asked to find out how much water and solids are present in 350 grams of fresh mangoes if their moisture content is 85% by weight. So the weight of the water will be equal to the weight of the sample times the moisture content as a decimal fraction. We have 350 grams of sample times 85% by weight as a decimal fraction, which becomes 0.85, and that works out to 297.5 grams of water. If there is 85% water in the mango sample, there will be 15% solids, and we got that by this relationship. We take 100% minus 85% water, which gives us 15% solids. So the weight of solids will be the weight of the sample times the solids content is a decimal fraction. Take 350 grams times 0.15, and that gives us 52.5 grams of solids present in that sample. You can also calculate the weight of solids in another way. Remember the relationship that the total weight will be equal to the weight of water plus the weight of solids. Writing that again, we can then rearrange this equation to give us the weight of the solids will be the total weight minus the weight of the water. If the total weight is 350 grams and the weight of the water is 297.5 grams, the difference of 52.5 grams will be the weight of the solids present. The following table lists the representative weight basis moisture contents of fruits and vegetables which you may encounter. These values are reliable averages. The actual moisture contents of samples that you may use may vary from these values, and this can be due to differences in growing conditions from those used to calculate the representative averages, and you may also see season to season variations in moisture content as well. So don't be surprised if your values do not agree exactly with those in the following table. Looking at this, we see that they are listed in alphabetical order starting with apples at 84% moisture. Cassava has a rather low moisture content of only 65% on a wet basis, and we can compare this to celery at 95% or eggplant at 93% moisture on a wet basis. In the second part of the table, we see jalapeno peppers with 94% moisture and radishes with 95% moisture by weight, but plantain has only 60% moisture on a wet basis. Potatoes have 78% moisture, and these refer to what are often termed Irish potatoes. In the final portion of the table, you can see that sweet green peppers have a moisture range from 92 to 94% wet basis moisture, and yams have only 69% moisture present in them. The wet basis moistures for other materials may be found online by searching for that particular product. Now let's take a look at problem-solving techniques. If it's a formal exercise, you should read the question thoroughly. Perhaps read it several times and be sure that you understand it. In real-life situations, you have to define your problem clearly so that you can define your objectives. Then you should begin by drawing a diagram of the system. I cannot emphasize this enough. I've shown it in red with capital letters and 5 exclamation marks, and still people refuse to draw diagrams, which could simplify the problem-solving process tremendously. Then we'll label the diagram and insert the things that we know on it. We can identify what we don't know and what we need to find out. We can try to establish relationships between the known and unknown quantities. Then we'll set up mathematical equations that we need for solving the problem. We'll approach the problem in a stepwise, organized manner, and this is key. You don't sit down to a meal and put everything into your mouth at once and try to chew it. You cut it up into manageable slices, and that's the same approach that you need to use when trying to solve a problem. Break it down into pieces or steps that are more manageable and easily solved. And above all, use dimensional analysis, which we will describe in more detail later. And of course, don't panic. And that's one of the beauties of using a diagram. It forces you to take a little bit of time to organize your thoughts, and it reduces that initial panic before you get into what I call the number crunching activities. So let's take a look at some drying calculations. The question asks us, how much product at 10% wet basis moisture would you obtain from drying 3.5 kilograms of carrot slices with an initial wet basis moisture of 89%? A second part of this question asks you how much water would be removed during the drying process. The problem has now been defined for us. we have to ask ourselves whether or not we understand what it is asking us to do. If so, we can begin by drawing a diagram of the system. This diagram does not have to be anything elaborate. In fact, the simpler the better. So let's begin by drawing a rectangle that we will label as being the dryer. We have a feed material going into the dryer, so we'll represent that by an arrow going into the dryer from the left-hand side, and we'll put on that what we know about the feed material. We know that we have 3.5 kilograms of carrots at 89.0% moisture. We also have product coming out of the dryer, so we'll label that with what we know. We know that it is at 10% moisture. We know that the product is dried carrots, but we don't know the weight, so we'll let the weight of the dried carrots be X kilograms. Now this doesn't describe everything that's going on because we also have some water removal, so we need to label that appropriately. We'll indicate it by an arrow leaving the top of the dryer, and we'll say that the water removed will be equal to Y kilograms. So you can see that we have a number of things here to determine. So where do we begin? Usually it is best to start with what you know about the most. Here we really only know about the feed material going into the dryer. So let's start there. The weight of the water in the feed will be equal to 3.5 kilograms times 89% moisture as a decimal fraction, which is 0.89, and that gives us 3.115 kilograms of water. And it's usually best to carry a few extra decimal places through the intermediate calculations, and then you can round off in your final answer. This way you avoid round off errors as you go through each of the individual steps. The percent solids will be 100% minus the percent water, which is 100% minus 89% water, or 11% solids. Then we can find the weight of the solids in the feed by taking the 3.5 kilograms, multiplying it by 0.11, which is 11% as a decimal fraction, and that gives us 0.385 kilograms of solids in the feed. We can now put these on our diagram. So you can look in the bottom left-hand corner and see that we have 3.115 kilograms of water and 0.385 kilograms of solids in the feed, and those two values must add up to 3.50 kilograms, which they do. Establishing the next relationship may not seem all that obvious at first. In drying, only moisture and perhaps a few other volatiles will be removed. Normally, no solids are lost unless some of the solids happen to fall through the wire mesh that you are using to hold the solids, or perhaps some of the solids get blown away by the drying air if it happens to be a light powdery material. But we can usually say that the weight of the solids going into the dryer will equal the weight of the solids coming out of the dryer. So let's restate this and say that this tells us that the weight of the solids in the product will be the same as the weight of the solids in the feed. Therefore, there will be 0.385 kilograms of solids in the product. And we can add this information to our diagram. And here it is shown in the bottom right-hand corner of the slide. We still do not know the value of X, which is the number of kilograms of dried carrots we're getting, nor do we know Y, the number of kilograms of water removed. But we're getting there. So we now know that there are 0.385 kilograms of solids in the product, and that the product contains 10% water, or 10% moisture. If the product contains 10% water, it will then contain 90% solids. And remember that you only have solids and water to worry about in most drying problems. So letting the weight of the product be X kilograms, we know that 90% of this amount is solids. We also know that the weight of these solids is going to be 0.385 kilograms. This tells us mathematically that 90% of x, which is 0.90 times x, will be equal to the weight of the solids, which is 0.385 kilograms. We can now solve for x by dividing 0.385 kilograms by 0.90, and that will give us 0.428 kilograms of product coming out of the dryer. If we have 0.428 kilograms of product and 0.385 kilograms of this is solids, then the difference between these two values must be water. So we have this equation that the weight of the water in the product is equal to the weight of the product minus the weight of the solids in the product. We can substitute the values there, which you have 0.428 kilograms of product minus 0.385 kilograms of solids, which means we must have 0.043 kilograms of water present in the product. And now we can add this to our diagram. Down in the bottom right hand corner we have the value of x, because we now know how much dried product we have, and we also know the amount of water that's present. So looking at the diagram, we can see that we have 3.115 kilograms of water in the feed material and 0.043 kilograms of water in the product, and we can now find y, the weight of the water removed. That's equal to the weight of the water in the feed minus the weight of the water in the product. That's equal to 3.115 kilograms of water in the feed minus 0.043 kilograms of water in the product. So we have to remove 3.072 kilograms of water, which is approximately equal to 3.07 kilograms of water. So the weight of the water removed, which is y, will be equal to 3.07 kilograms. There is also another way to find the weight of the water removed. Since only water is lost in the process, we can take the weight of the feed material going into the dryer and subtract the weight of the product coming out of the dryer. So the weight of water removed is the weight of the feed material minus the weight of the product. Here you see the values. That gives us 3.072 kilograms, which is approximately equal to 3.07 kilograms of water removed. And that's the same answer that we obtained earlier. Adding this to the diagram, we get the full picture. 3.07 kilograms of water are removed, giving us 0.428 kilograms of product in total, and that will have a 10% wet basis moisture. So summarizing, we now know that we will get 0.428 kilograms of product, and we will have to remove 3.0 kilograms of water in the dryer to do this job. There is a convenient shortcut that you may want to know about for figuring out the weight of the final product when you are targeting for a certain final moisture. Step 1 is to take the final moisture as a decimal fraction and subtract it from 1.00. 1.00 is the decimal equivalent of 100%. Then we divide the weight of the solids in the initial material by the value that we obtain in step 1. If you are targeting for 10% moisture in your final product, the value from step 1 will be 0.90. This is 1.00 minus 10% moisture as a decimal fraction, which is really giving you the percent solids as a decimal fraction, and that decimal fraction is 0.90. Now I'd like to warn you about a common trap into which people fall. Some people say that they have 3.5 kilograms of feed and they are reducing the moisture content by 80%. That is, they say they have 90% moisture in the feed material and that they have 10% moisture in the final product. So they just take 80% of 3.5 kilograms as the amount of water removal. This gives them 2.8 kilograms of water removed, which is totally and completely wrong. So let's put a big stroke through this to emphasize the point. Thank you very much.